The meat of this lecture today is going to be about the big three. All right, and the big three are greenhouse gases that are infrared opaque. They absorb infrared. So in my notes, I've got this labeled as big three, and these are infrared absorbers. We're going to go through water, CO2. All right, so it's H2O. This is the most important of the three. That might have surprised you. You might have thought of CO2, but this I'm gonna actually make you write it down too. This is most important, but it is regulated by itself in such a way that it ends up not being the most important. Am I putting a contradiction right at the start of my lecture? Okay, but I'm okay with you thinking about it that way. So it is the most important. It has a huge, and maybe even we could say largest, greenhouse effect. It definitely occurs in the largest abundance in our atmosphere. It occurs from, it's 0 to 5 weight percent of our atmosphere is H2O. And you have felt that before because it is water moisture, it is water vapor. A lot of times we just call this humidity. And one thing you know about humidity is that humidity changes over the course of a day, over a course of a season, or with geography. And it's this process that changes humidity, right, which is weather and rain, precipitation, cloudiness, that is the self-regulating effect that makes H2O maybe a little bit less important than I initially started to claim. So what we're going to say here is when the water levels are high, we're going to have rainfalls. Rainfalls at high H2O. And so what this process does is it self-regulates. We never in our atmosphere get so high that we get tons and tons of IR absorbance, because once we get super high, then the rain starts to fall. Now, what's interesting is there's another really important feedback with water, and I guess that's this concept here of self-regulation. You could also write the word feedback in. So here's a fact. 1 degree Celsius hotter atmosphere can hold 7% more H2O. So if climate gets hotter, more water can be stored in that climate. But you know what happens when you have more water? If you have more water, you have more clouds. If you have more clouds, then you have more albedo. All right, that means there's less energy coming from the sun. If you have more albedo, then you are cooler. If you're cooler, then you have less humidity because you can hold less water. If you have less humidity, then you have less clouds. Oh, does this feel circular? Maybe I could have even drawn it where it was like this very circular kind of argument. And that's the key to water, is that it is the self-regulated cycle with positive and negative feedbacks. The other thing I want you to know about water, and we're going to put it here, is we're just going to put the word complicated. This is one area within the scientific community that is somewhat contradictory and does require more study. You'd think it would have been studied exceptionally well, but really it's CO2 and methane that are better understood than water. All right, going back to last time with our energy diagram from Earth and energy. And what was this down here? This was wavelength going from 5 to 50 microns. This is the energy that the Earth wants to absorb, and the energy that the Earth actually absorbed is something like this instead. It's this domain here, and it's this domain here that is, these are the wavelengths, the bands that water absorbs. How does water absorb it? Okay, that's a good question. Thanks for asking. H2O. Well, the molecule of H2O looks like this. It's a polar molecule with the H's on one side. And when IR energy hits this molecule, these wings start to move. And they actually move in a lot of different ways. They start to vibrate up and down like birds' wings. They extend back and forth with stretching, and they even well, I guess we'll just say this. They vibrate, they bend, and they stretch. The bonds do, okay? It's these bonds right here. This and this changes its length and changes its angle. And that change absorbs energy. And that's why water absorbs infrared. Okay, that's water. Now let's do CO2. This is kind of where the meat of the lecture is going to be. And you experience, right, if we experience water in the form of humidity, we experience CO2 in our daily life as well, but much less so. It's dense, odorless, colorless gas. It's in our atmosphere at the ppm level, which is very low abundance. And the place where you see it the most would be like in a Coke or in a soda as that fizz. In fact, we'll just put the word fizz here to make that connection. Now, the ppm level that currently is in our Earth's atmosphere is 420 ppm. And I want to just think about what that means. So if 420 ppm, that's 420 parts for every million parts. That's what that measurement means. So 420 parts for every million parts. And we can turn that into a percentage by just going over, let's see how we can do this. We go over 1, 2, 3, 4. That would put the decimal point here at 100. We can turn it into a percentage. So to do that, we'd have to go over 1, 2, 3, 4 to put the decimal there. So then that's the number. So with that conversion of units from 420 ppm, that equals a 0.04%. 0.04% is an incredibly small number. Can something with that small of a number actually have an impact? The answer is yes. When you have 0.04, we could do this like analogy. And maybe this isn't a great analogy for a college class, or maybe it's a great one, I don't know. But the analogy here would be blood alcohol level. The blood alcohol level. If you have a blood alcohol level of 0.04, you're starting to feel the effect of the alcohol. Maybe you'd say like you're buzzed. And a blood alcohol level of 0.08% is where you're going to get a ticket in the state of Texas. That's where you're driving under the influence. And that's from just about 3 to 4 beers. So this is, I think, is a good example of showing that 0.04% can have an impact even though it's such a small concentration, if the thing is powerful. And it is powerful. Well, alcohol and CO2, both are powerful things. In fact, CO2 accounts for approximately 65% of the greenhouse effect. And that's a pretty wild thing to make a connection that 420 ppm, 0.04 weight percent, can actually contribute 65% of the overall greenhouse effect. And the reason for that is that CO2 is 20 times more absorption of IR. I spelled it wrong. Oh boy, real bad. Absorptive than water. So even though it's in such a small concentration, it is super absorptive. And its absorption in the same way. It has to do with the molecular bonds. And so it's C and O. These are the bonds. And these bonds here between C and O, they absorb IR energy. And they specifically do it by stretching. So you can imagine these O's bouncing back and forth, like from this distance down to this distance, back and forth, back and forth, back and forth, back and forth. And that is what is absorbing our energy. In terms of our graph of Earth's emissions and where does CO2 have that effect, we could draw that again. There's energy. Here's the graph of the ideal. The graph of the real is something like this, right? That's not very technical, but here it's this band is where CO2 is having its influence. Next big concept I want to talk to you about is like, how are we measuring CO2 and where are we measuring it? Well, it's this graph. This graph is called the Keeling curve. We're going to label this. This is called the Keeling curve, and it's named after a scientist who started making the measurements and recognized that it is a curve. And so what I want you to check here, of course, is the x and y axis. Every time I show you the graph, these are years here on the x, and so today is down here, and we would say this is at, here is our 420. And what Keeling discovered through this science is that the amount of CO2 in the atmosphere is increasing by around 2 ppm per year. And you can work this backwards in time, and if we were to take this even back further in time, we get to before the Industrial Revolution, before we started burning fossil fuels, it was 280 ppm. And that's going to be plus or minus about 10 ppm, and this is from ice cores. These are from proxies. The actual, so this would be like 1850, before 1850, this is what it was at. We started actually measuring right around 1920, but the Keeling curve starts there at 1960. One of the neat things about the Keeling curve, if we were to like draw a box right here and zoom in, is that there's this zigzag. Okay, how do we do this? There it is. Here's the pattern that we see on this really consistent pattern. And this bottom part right here, this is end of summer. Because over the course of the summer, CO2 concentration goes down as everything green flourishes. And so CO2 actually goes down every single year across Earth in any specific place, and on an average, it goes down a little bit, and then it jumps back up, and it goes back down as things grow again. So we could say like this is like plant growth is what makes the drop occur. CO2 is like an atmospheric fertilizer in some ways. Now this value of 420 ppm, this is actually the highest in 2 million years if we look back into proxies. 2 million years, this is the highest value. It has certainly varied throughout history, but we're at a really high point, and it is probably, well, it is because we are adding so many, we're adding so much CO2 by burning fossil fuels. Okay, there is my introduction to you of CO2, and now let's get into the last of the big three, which is methane, which is CH4. All right, so methane, how do you interact with methane? We'll write that down here. You interact with methane in your day-to-day life by cooking and electricity. In some places, we get our electricity by burning methane. Sometimes we cook our food by like the blue stove, the blue flame on a stove. That is methane, or maybe technically it could be propane. Propane's the same thing as methane, except for it has like this a couple more C's and a couple more H's. But anyways, we're not talking about propane. I was just trying to make a connection to your real life. We're talking about methane. All right, natural gas. That might be a way to think about what is, well, okay, natural gas. Now, what's crazy about methane is that its concentration in our atmosphere right now is 1900 parts per billion. That's even way smaller than 420 parts per million. But this is up from a background, like if we look back into our proxies deep into geologic time, the background rate before the Industrial Revolution is around 700 plus or minus 400 parts per billion. So definitely the 1900 is high, and it's from burning fossil fuels and a few other things. All right, so this is measured from ice cores, by the way, as a proxy. We think that methane contributes about 10% to the overall greenhouse effect. 10% of overall greenhouse effect. So it's much less than CO2, right? CO2 was 65%. But still a significant contributor. The reason for why something at 1900 ppb can contribute 10% is that because it is way more powerful in terms of absorptivity. It's 1400 times more absorptive than H2O. So even though it's in a very small, we could say small but powerful. That's the story with methane. What's cool about methane, okay, I'm giving you some facts here, is that it has a washout. I we need to go back to CO2. We didn't talk about CO2's washout. Water has a washout that is every 9 days. Methane has a washout that's about every 9 years. So we put methane into the atmosphere, it washes out in 9 years. I didn't do that for CO2. Let me scroll back up to CO2. CO2's washout, this is the problem with CO2. The washout is like more than 1,000 years. That's why when we put CO2 into the atmosphere, the Keeling curve is only ever going up, 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 because we don't actually get a washout. Water's washout's actually every 9 days, right? Because of the precipitation rain. All right, so we've been showing this graph each of the times with energy, and this is Earth, and this is wavelength going from 5 to 50 microns, and there's the ideal graph, and then there's the actual graph. It's this area right here, kind of overlapping with water, where CH4 has its impact. That's where methane. So in this one we keep skipping is ozone. I'm just not going to teach about ozone. It is also a greenhouse gas that matters, but I'm got to pick and choose. Now the formation of methane is twofold. Formation of methane is from burning fossil fuels. If we wanted to reduce the amount of methane in our atmosphere, we would burn less of them. So this is like burning natural gas, burning gasoline, burning coal, burning oil, fossil fuels. And then the other one is called enteric fermentation. Enteric fermentation. I'm giving you this scientific term because this is a scientific class, but this enteric means digestion and fermentation means fermentation. So this is from livestock and from landfills, from the gases that are being built up from the decay of matter in their gut or just in the landfill. So enteric fermentation is livestock and landfills. It's a pretty neat formation. The fact that like our cows and cattle and our sheep can actually be contributing to global warming is an interesting concept.